Hello there and welcome back to the Science Sleepy Minds. Tonight you are floating. Not metaphorically, not poetically. Well, okay, a little poetically. But right now, in your mind's eye, you are suspended in the blackest, quietest stretch of nothing you have ever experienced. There is no up. There is no down. There is only the faintest prickling of ancient starlight against your closed eyelids, pinpricks so old that the civilizations which might have orbited those stars have long since turned to dust. And somewhere out there, hiding in a patch of sky no bigger than a grain of sand held at arm's length, is a galaxy that should not exist. Not probably shouldn't. Not is a little surprising. Flat out, textbook-defyingly, career-threateningly should not be there. And yet there it is, glowing stubbornly in the infrared, daring every astrophysicist on Earth to explain it. You probably won't survive this entire journey awake. Most people tap out somewhere around the dark matter halos, but that is perfectly fine. That is the whole point. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. Drop a comment telling me where you're listening from and what time it is where you are. I always love reading those. Someone last week was tuning in from a fishing boat off the coast of Norway at 2 a.m, which honestly sounds like the most atmospheric way to fall asleep to cosmology. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You settle deeper into whatever soft surface is cradling you right now, and the darkness behind your eyelids becomes the darkness of intergalactic space. Not the friendly darkness of your bedroom, but something vaster, something so immense that your brain quietly declines to process it, and instead offers you a gentle feeling of weightlessness as a consolation prize. You're drifting in the void between galaxy clusters, a place where the nearest meaningful chunk of matter might be tens of millions of light years away. This silence here is absolute. Not the silence of a quiet room where you can still hear blood pulsing in your ears, but a silence so total it almost has texture, like velvet pressed softly against your thoughts. And this is where the story begins. Not with a bang, not with a dramatic orchestral swell, but with a question, a very simple question that turned out to be extraordinarily difficult to answer. What was the universe doing in its first few 100 million years? For most of the history of astronomy, that question was essentially academic. We had theories, we had elegant mathematical models, we had computer simulations that churned through billions of virtual years and spat out tidy predictions about how the first stars sparked to life, how those stars clumped into baby galaxies, and how those baby galaxies slowly, patiently, merged into the grand spirals and ellipticals we see today. The story was neat. The story was satisfying. The story was, as it turns out, almost certainly incomplete. The problem with studying the earliest epochs of the universe has always been one of technology. The light from those primordial objects is phenomenally faint. It has been travelling for over 13 billion years, stretched by the expansion of space itself from the visible spectrum deep into the infrared. To see that light, you need a telescope unlike anything ever built. You need a mirror so large and so precisely shaped that if you scaled it up to the size of the continental United States, the biggest imperfection would be roughly the height of a blade of grass. You need to park that mirror 1,000,000 miles from Earth at a gravitational sweet spot called the second Lagrange point, where it can hide from the sun's glare behind a sun shield the size of a tennis court. You need to cool its instruments to temperatures colder than anything naturally occurring in our solar system, so cold that the telescope's own heat does not drown out the whispers of ancient photons. You need, in short, the James Webb Space Telescope, and for a long time, you did not have it. For a torturously long time, in fact. Astronomers proposed the concept in the late 1980s, back when the Hubble Space Telescope had not even launched yet. The original budget was around $1 billion. The original launch date was somewhere around 2007. If you know anything about JWST, you already know that neither of those numbers survived contact with reality. But all of that headache and heartbreak and congressional testimony is a story for the next stretch of our journey. Right now, you're just floating here in the dark, breathing slowly, letting the enormity of the question settle around you like a blanket. Somewhere in this void, there is a galaxy that formed so quickly, so massively, so defiantly early, that when its light finally reached a golden mirror orbiting a small rocky planet in an unremarkable spiral galaxy, it broke the models. Scholars still argue whether this single discovery represents a crack in the foundation of modern cosmology or merely a missing chapter, a blind spot that was always there, waiting for eyes sharp enough to see it. Tonight, you are going to find out. Or, more likely, you're going to fall asleep trying, and honestly, either outcome is a win. The stars around you seem to dim just a fraction, as if the universe itself is lowering the lights for you. The story of how humanity built the most expensive scientific instrument ever launched into space is, depending on your temperament, either an inspiring testament to human ambition or a cautionary tale about what happens when engineers say yes to every single upgrade. You're still drifting out here in the dark, but now you're drifting backward through time, back to the late 1980s, back to a period when the Hubble Space Telescope was still sitting in a clean room being fussed over by technicians in bunny suits. Hubble had not yet launched. It had not yet delivered its first blurry images. It had certainly not yet had its famously flawed mirror diagnosed and corrected by what amounted to a celestial pair of spectacles. And yet, even before Hubble left the ground, a small group of astronomers was already thinking about what would come next. You have to admire that kind of forward planning, or maybe you have to be slightly concerned by it. Either way, in 1989, the Space Telescope Science Institute convened a workshop grandly titled the Next Generation Space Telescope. The idea was straightforward in concept and nightmarish in execution. Hubble saw primarily invisible and ultraviolet light, but the most distant, most ancient objects in the universe emit their light in the infrared, because the expansion of space has stretched their original wavelengths far beyond what human eyes or Hubble's instruments could detect. So the next great telescope would need to see in the infrared. And to see in the infrared with any real sensitivity, it would need to be cold, brutally, absurdly, almost philosophically cold. Because infrared radiation is essentially heat radiation, and a warm telescope trying to detect faint infrared signals from the edge of the universe is a bit like trying to listen to a whisper while standing next to a jet engine. You need to eliminate your own thermal noise. The original concept called for a mirror about 4 meters across, roughly twice the diameter of Hubble's. The estimated cost was around $500 million. The proposed launch date was 2007. If you're doing the math in your head right now and comparing those numbers to what actually happened, you are probably smiling in the dark, and you should be, because what followed was one of the most spectacular cases of scope creep in the history of engineering. The mirror grew, first to 6 meters, then to 6.5, a honeycomb mosaic of 18 hexagonal segments, coated in a microscopically thin layer of gold, because gold happens to be an excellent reflector of infrared light. This is one of those facts that makes gold enthusiasts feel very validated. The sun shield expanded to 5 layers of a material called Captain, each thinner than a human hair, designed to unfold in space like some kind of cosmic origami. The instrument suite became more sophisticated, the cooling systems became more elaborate, and the budget began its slow, relentless march upward. 1 billion became 2, 2 became 3, 3 became 5, 5 became 8. By the time the final tally was calculated, the James Webb Space Telescope had cost approximately $10 billion and was running about 14 years behind schedule. There's a quirky little anecdote from the mid-2000s when the project was in such dire financial straits that Congress nearly cancelled it entirely. The House Appropriations Committee actually voted to zero out JWST's funding in 2011. It took a massive lobbying effort by the scientific community, some deft political manoeuvring, and what several insiders have described as sheer institutional stubbornness to get the project reinstated. Astronomers sometimes joke that JWST's greatest engineering challenge was not the mirror or the sunshield, but surviving the budget process. And yet, through all of those years of delays and cost overruns and very tense meetings in conference rooms with bad coffee, the fundamental scientific case for the telescope never wavered. The universe was out there, hiding its earliest chapters in wavelengths of light that no existing instrument could properly read. Hubble had done heroic work. It had peered back to within about 400 million years of the Big Bang and found tantalizing hints of early galaxies, fuzzy red smudges at the very edge of its detection capability. But Hubble was straining. It was like trying to read a novel by holding it at the far end of a football field. You could tell there were words on the page, but you could not make them out. JWST was designed to walk you right up to the book and hand you a magnifying glass. There is a historical parallel that astronomers love to draw, and it is worth lingering on for a moment as you settle deeper into your pillow. When Galileo first pointed his crude telescope at Jupiter in 1610, he saw 4 tiny points of light that moved from night to night. He had discovered Jupiter's largest moons, and in doing so, he shattered the prevailing model of the universe, the one that placed Earth at the centre of everything. Galileo did not set out to break cosmology, he was just looking. And that is exactly what JWST was designed to do. Just look. But look deeper, look further, look more carefully than anything before it. The astronomers who championed the project knew they would find surprising things. They always do. What they did not fully anticipate was just how surprising those things would turn out to be. The telescope was finally assembled, tested, folded up like the most expensive piece of flat-pack furniture in human history, and loaded into the cargo fairing of an Ariane 5 rocket in Kourou, French Guiana. The launch date was set for December 25, 2021, Christmas morning. Scholars still argue whether the choice of Christmas Day was a deliberate bit of symbolism, a gift to humanity, a new star in the east, or simply the date that happened to work out on the launch manifest. Either way, it meant that thousands of astronomers around the world spent that particular holiday not opening presents, but clutching their phones, refreshing live streams, and trying very hard not to think about the 344 single points of failure that all had to work perfectly for the telescope to survive its journey. You're breathing slowly now, letting the numbers wash over you without grasping too tightly at any of them. $10 billion, 18 golden mirrors, 5 layers of sunshield, 344 ways it could all go wrong, and 1 million miles of empty space between Earth and the telescope's final destination, a place where no repair mission could ever reach it. If something broke, that was it. The most expensive scientific instrument ever built would become the most expensive piece of space debris ever created. The rocket engines ignited on Christmas morning, and the telescope rose into the sky on a pillar of fire. The pillar of fire thinned and vanished, and the telescope was alone. You can picture it if you like, a golden origami butterfly folding itself open in the silent dark, each deployment step monitored by engineers on the ground who had rehearsed these sequences thousands of times, but who were now, for the first time, watching them happen for real, a million miles away, with no possibility of a do-over. The sunshield unfurled first, 5 gossamer layers stretching taut like the sails of some impossibly delicate ship. Then the secondary mirror swung into position on the end of its tripod boom. Then, one by one, the 18 hexagonal mirror segments unfolded and locked into place, each one adjusting itself with nanometer precision using tiny actuators on its back. The whole process took about 2 weeks, and during those 2 weeks, the collective blood pressure of the astrophysics community probably set some kind of medical record. But it worked. Every single deployment step, all 344 of them, executed flawlessly. The telescope drifted into its halo orbit around the second Lagrange point, a gravitationally stable spot where the Sun, Earth and Moon are all behind the sunshield, leaving the mirror staring into unobstructed darkness. The instruments cooled, the mirrors aligned, and then, in the early months of 2022, the first test images started trickling back to Earth. They were calibration images technically, not meant for public consumption, just engineers checking focus and alignment by pointing the telescope at a random star. But even those calibration shots made astronomers gasp, because in the background behind the target star, you could see galaxies, hundreds of them, thousands, tiny spirals and ellipticals scattered across the frame like luminous confetti, each one containing billions of stars, many of them never seen before by any telescope. And this was just the background noise of a test photo. It was like buying a new pair of glasses and realizing you can suddenly read the serial numbers on satellites. The real show began on July 12th, 2022, when NASA released the first official batch of full-color science images from JWST. You may remember where you were that day. A lot of people do. The first image was unveiled by President Biden at a White House event the evening before, which gives you some sense of how significant the moment was considered to be. It was a deep-field image of a galaxy cluster called SMACS 0723, and it showed a region of sky that to the naked eye would appear completely empty, a tiny dark patch roughly the size of a grain of sand held at arm's length. But through JWST's golden eye, that patch was blazing with light. Galaxies upon galaxies upon galaxies, some of them warped and stretched into elegant arcs by the gravitational lensing of the foreground cluster, their light bent by the curvature of space-time itself. The image contained objects whose light had been travelling for over 13 billion years. You were looking at the universe as it existed when it was less than 5% of its current age. The response was immediate and overwhelming. Social media lit up. Astronomers posted the image side by side with Hubble's old deep field shots, and the improvement was almost comical. Where Hubble had seen a few faint red smudges, JWST saw fully resolved structures, spiral arms, bright cores, satellite companions. It was as if someone had wiped a fogged windshield and revealed an entire cityscape that had been there all along, just hidden behind the blur. There is a fun little detail that circulated online in the days after the release. One of the tiny red dots in the SMACS 0723 image was initially misidentified by an amateur astronomer on Twitter as a potentially record-breaking distant galaxy. It turned out to be a much closer, much less exciting object that just happened to be very red. The incident became a gentle running joke about the dangers of doing astrophysics by social media, but it also illustrated something important. People were hungry for this. They wanted to see what was out there. They wanted to know. And what was out there, it turned out, was trouble. Beautiful, magnificent, paradigm-rattling trouble. Because as the science teams began processing the data from JWST's first deep surveys, programs with names like JADES, SEERS, GLASS and Cosmos Web, they started finding objects that did not belong. Galaxies at redshifts so high that they should not have had time to form. galaxies so massive and so luminous that the standard models of cosmic evolution simply could not account for them. Not struggled to account for them. Could not. The math did not work. The timelines did not add up. The universe, it seemed, had been far busier in its infancy than anyone had predicted. Scholars still argue whether the shock was genuine, or whether some theorists had quietly suspected for years that the standard picture of early galaxy formation was too tidy. There had been hints, after all. Hubble had found a handful of surprisingly bright objects at very high redshifts, and a few papers had cautiously suggested that early star formation might have been more efficient than models assumed, but those were whispers. What JWST delivered was a shout, and the loudest shout of all came from a tiny ancient smudge of reddened light lurking in the JWST survey data, an object so distant that its photons had been travelling since the universe was barely 300 million years old. You feel the weight of that number settle over you like a second blanket. 300 million years. In cosmic terms, that is nothing. The universe is 13.8 billion years old. 300 million years after the Big Bang is like the first 15 minutes of a very long movie, and somehow, in those first 15 minutes, something enormous had already assembled itself in the dark. Your breathing slows. The golden mirror hangs in your mind's eye, patient and silent, collecting photons that have been in transit since before the Earth, the Sun, or even the Milky Way existed in their current forms. That tiny smudge has a name, and it is not a particularly romantic one. You're not going to find it embroidered on throw pillows or whispered in love poems. It is called JADES, GSZ130, which sounds less like a celestial object and more like a printer model number. But that is how astronomy works. The poetry is in the light, not the label. JD stands for the JWST Advanced Deep Extragalactic Survey, one of the telescope's flagship observation programs, designed to stare at two specific patches of sky for an extraordinarily long time, soaking up every last photon like a sponge held under a dripping faucet. The GS indicates it was found in the Good South Field, a well-studied region of sky near the constellation Fornax. The Z13-0 part tells you its redshift, and that is where things get interesting, because a redshift of 13 is not just high, it is absurdly, almost incomprehensibly high. You're lying there in the dark and you might be wondering what a redshift of 13 actually means, in terms you can feel rather than calculate. So let yourself sink a little deeper into the mattress and picture this. Imagine you're standing on the shore of a vast calm lake. You toss a pebble into the water and a ripple spreads outward in a perfect circle. Now imagine that while the ripple is spreading, the lake itself is expanding. Not just the water flowing outward, but the actual fabric of the lake stretching in every direction. The ripple is still moving, but the distance it has to cover keeps growing. By the time it reaches the far shore, it has been stretched out. What started as a tight, compact wave is now a long, lazy undulation. That is what happens to light travelling through an expanding universe. The wavelength gets stretched. Blue light becomes red light becomes infrared, and if the journey is long enough, visible light gets stretched so far into the infrared that no human eye could ever detect it. You need a golden mirror parked at the second Lagrange point. A redshift of 13 means that the light from JD's GSZ13-0 has been stretched by a factor of 14. The wavelengths you are detecting are 14 times longer than the wavelengths originally emitted, and when you run that number through the equations that describe the expansion history of the universe, you get a travel time of approximately 13.4 billion years, which means this galaxy existed when the universe was roughly 320 million years old. Let that settle. 320 million years. The universe itself is 13.8 billion years old, So you're looking at something that existed when the cosmos was about 2.3% of its current age. If the universe were a human life of 80 years, this galaxy showed up in the first 22 months. It is a toddler building a skyscraper, and it is not a wispy, barely there smear of a few young stars, which is what the models predicted you should find at that epoch. The model said that at 300 million years after the Big Bang, the universe should contain, at best, small clumps of gas just beginning to condense, proto-galaxies in the most embryonic sense, tiny seeds that would take billions of additional years to grow into anything recognizable. What JWST found instead was a galaxy with a substantial stellar mass. Estimates vary depending on which team does the analysis and which assumptions they feed into their models. But the numbers that kept appearing in the early papers were on the order of hundreds of millions of solar masses in stars. Some estimates push toward 1 billion. 1 billion solar masses worth of stars already formed, already shining, already assembled into a coherent structure at a time when the universe was barely old enough to have produced the raw materials. This is where the word impossible started appearing in headlines. And while scientists are generally cautious about that word, preferring phrases like insignificant tension with current models, the popular press had no such reservations. The galaxy that shouldn't exist became the shorthand, and honestly, it was not that far off. Within the framework of the standard Lambda CDM cosmological model, the model that has successfully described the large-scale structure and evolution of the universe for decades, a galaxy this massive, this early, is not merely unlikely. It is, in the strictest statistical sense, not supposed to happen. The probability distributions do not extend that far. It is like rolling a die and getting a 7. The face does not exist on the object you are holding. And yet there it was, captured in JWST's near-infrared camera, a cluster of photons that had been travelling through expanding space for over 13 billion years. Photons that were emitted as bright ultraviolet light by hot young stars and arrived at the telescope as faint infrared whispers. There is something almost tender about that, if you let yourself feel it. Those photons left their source when the universe was a dark, formless place, mostly hydrogen and helium, and the invisible scaffolding of dark matter, and they arrived at a mirror built by a species that would not evolve for another 13 billion years on a planet that would not form for another 9 billion years after that. The photons were older than the ground beneath your house, older than the sun, older than the concept of ground. Scholars still argue whether JADESGSZ 13-0 represents the single most challenging object for standard cosmology, or whether it is merely the most famous member of a larger population of early galaxies that collectively pose the real problem. Because as you will discover if you manage to stay awake a little longer, it was not alone. It was not even the strangest thing JWST found in those first frantic months of data. But it was the one that landed first, the one that cracked the door open, the one that made astronomers look at each other across conference tables and say, with varying degrees of excitement and dread, "We might have a problem." Your eyelids feel heavier now, and that is fine. The galaxy does not mind. It has been waiting 13 billion years for someone to notice it. It can wait a little longer while you settle in. You're sinking now, slowly, comfortably, the way a leaf sinks through still water, and as you drift, let yourself think about light. Not the light from your phone screen, not the light leaking under your bedroom door, but light as a thing that travels. Light as a messenger. Light as the only witness to events so distant that by the time its testimony arrives, the scene of the crime has changed beyond all recognition. Everything you know about the universe beyond your own solar system, you know because of light. Not because someone went there, not because someone sent a probe, because photons left a source, crossed unimaginable distances and happened to land on a detector that a clever species of primates built and pointed in the right direction. That is it. That is the entire observational toolkit of cosmology. Photons and patience. And the single most powerful trick astronomers have for reading those photons is redshift. You heard the word a moment ago when we talked about JWST 13.0 and its redshift of 13, but now let yourself really understand it, not as a number, but as a sensation. Imagine you're standing beside a railroad track. This is the classic analogy, and it is classic because it works. And a train is approaching you with its horn blaring. The sound waves are compressed as the train moves toward you, so the pitch sounds higher. Then the train passes and moves away, and the sound waves are stretched out behind it, so the pitch drops lower. That is the Doppler effect, and you have heard it 1,000 times in your life without thinking about it. Redshift is the Doppler effect's cosmic cousin, but with a crucial twist. When an ambulance drives past you, the ambulance is moving through space. The medium, the air, stays put while the source moves. But in cosmology, the galaxies are not really moving through space in the traditional sense. Space itself is expanding. The galaxies are more or less sitting still, like raisins in a loaf of bread that is rising in the oven. The raisins are not crawling through the dough. The dough is stretching, and the raisins are being carried apart by the expansion. So when light travels from a distant galaxy to your telescope, it is not being Doppler shifted by the galaxy's motion. It is being stretched by the expansion of the space through which it travels. The longer the journey, the more stretching occurs. The more stretching, the redder the light becomes, and if the journey is long enough, the light redshifts entirely out of the visible spectrum and into the infrared. This is why JWST was built to see in infrared. The most ancient light in the universe has been stretched so far that it is invisible to optical telescopes. Hubble could catch the near-infrared, the light that has been only moderately stretched, and it did heroic work at those wavelengths. But the truly ancient stuff, the light from the first few 100 million years, is deep infrared, and for that, you need JWST's gold-coated mirrors and cryogenically cooled detectors. Gold, by the way, is used not because it is pretty, though it undeniably is, but because gold is exceptionally good at reflecting infrared wavelengths. A thin coating of gold, about 1,000 atoms thick, turns each mirror segment into an almost perfect infrared reflector. There is a quirky historical detail here that is worth savouring. The total amount of gold on all 18 mirror segments combined is about 48 grams, roughly the weight of a golf ball, $10 billion, and the gold component would fit in your palm. Astronomers have occasionally noted that this makes JWST's gold the most expensive gold per gram in human history, beating out even the most overpriced jewellery on the planet. Now, the reason redshift is so powerful as a tool is that it gives you distance, and distance in an expanding universe gives you time. If you measure a galaxy's redshift and you know the rate at which the universe has been expanding, which cosmologists have spent decades painstakingly calibrating, using everything from supernovae to the cosmic microwave background, you can calculate how far away the galaxy is, and more importantly, how long its light has been travelling. A redshift of 1 means the light has been travelling for roughly 7.7 billion years. A redshift of 5 gets you to about 12.5 billion years. A redshift of 10 pushes you back to about 13.2 billion years, when the universe was only about 500 million years old. And a redshift of 13, the territory where JWST 13.0 lives, puts you at roughly 13.4 billion years of travel time, corresponding to a universe barely 300 million years old. But here is the thing that makes redshift measurements tricky, and this is important for the drama that unfolds later. There are 2 main ways to measure redshift. The first is photometric redshift, which is essentially an educated guess. You take an image of a galaxy through several different filters, each sensitive to a different range of wavelengths, and you look at how bright the galaxy appears in each filter. Then you compare that pattern of brightnesses to what you would theoretically expect for galaxies at various redshifts, and you pick the best match. It is like trying to identify a song by hearing only a few notes played on a muffled speaker. You can usually get close, but you can also get fooled. The second method is spectroscopic redshift, which is far more precise. You spread the galaxy's light into a full spectrum, identify specific emission or absorption lines, the chemical fingerprints of hydrogen, oxygen, carbon, and measure exactly how far those lines have been shifted from their laboratory wavelengths. This is like hearing the full song in high fidelity. There is no ambiguity. The early JWST discoveries, the ones that made headlines, were mostly based on photometric redshifts. And that distinction, as you will find out, became the centre of a heated and occasionally personal debate among astronomers who were either thrilled or terrified by what the data seemed to be saying. Scholars still argue whether the initial excitement was premature or perfectly justified, but either way, the photons had spoken. The question was whether anyone was reading them correctly. Your breathing has settled into a rhythm now, slow and deep, and the railroad track has faded from your imagination, replaced by the quiet hum of expanding space, stretching ancient light into longer and longer waves, like a lullaby being played at half speed. The light is still stretching, and so are you, loosening into the quiet, letting your thoughts unspool like thread from a bobbin. And now you need a map. Not a spatial map, not a chart of where things are, but a temporal one. A map of when things happened. Because to understand why a galaxy at redshift 13 is such a problem, you need to know what the universe was supposed to be doing at that age, and to know that, you need to walk through the cosmic timeline as astronomers understood it before JWST came along and scribbled all over it with a red pen. You start at the beginning. Not the very beginning, because the very beginning is a mathematical singularity that physics cannot actually describe, and thinking too hard about it at this hour might wake you up. But you start at the first fraction of a second, when the universe was unimaginably hot, unimaginably dense, and expanding at an unimaginable rate. In the first 3 minutes, and this is one of the great triumphs of 20th century physics, the temperature dropped enough for protons and neutrons to fuse into the lightest atomic nuclei. Hydrogen, mostly. A good deal of helium, a tiny sprinkle of lithium, and that was it. No carbon, no oxygen, no iron, no gold. Just the 3 simplest elements, forged in a cosmic furnace that cooled too quickly to cook anything heavier. This process, called Big Bang nucleosynthesis, was first described in detail in a landmark 1948 paper by Ralph Alpher and George Gamow, who famously added Hans Beth's name to the author list purely so it would read Alpha Beth Gamow, a pun on the first 3 letters of the Greek alphabet. Physicists have always had a peculiar sense of humour. For the next 380,000 years the universe was opaque. All that hydrogen and helium existed as a hot plasma, a soup of free electrons and nuclei that scattered photons the way fog scatters headlights. Light could not travel in a straight line. It bounced and ricocheted and went nowhere useful. Then, around 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with nuclei and form neutral atoms. This event is called recombination, which is a slightly misleading name since the electrons and nuclei had never been combined before, but astronomers were apparently not consulting the linguistics department that day. When recombination happened, the fog cleared. Photons were suddenly free to travel unimpeded, streaming across the universe in every direction. Those photons are still travelling today. They have cooled and stretched over 13.8 billion years into faint microwave radiation, and they form the cosmic microwave background, the oldest light you can detect, a snapshot of the universe as a baby. Smooth and hot and featureless except for tiny, tiny ripples in temperature and density. Those tiny ripples are everything. They are the seeds of all structure. Slightly denser regions had slightly stronger gravitational pull, so they attracted a little more matter, which made them denser still, which attracted even more matter. Over millions of years, this process, gravitational instability, the slow, patient victory of gravity over expansion, began to sculpt the smooth early universe into something lumpy. But the process was agonizingly slow, at least according to the standard model, and after recombination came a period that astronomers call the Cosmic Dark Ages, which is exactly as dramatic as it sounds. There were no stars, there were no galaxies, there was just gas, hydrogen and helium cooling and drifting in the dark, slowly condensing into denser filaments and knots under the guidance of dark matter, which had been quietly doing its gravitational work since long before recombination. Dark matter, that invisible scaffolding that makes up roughly 27% of the universe's total energy content, does not interact with light. It does not glow. It does not absorb. It does not scatter. It only gravitates. And because it only gravitates, it was free to begin clumping even while the ordinary matter was still trapped in the hot plasma fog. By the time recombination freed the ordinary matter, dark matter had already built a web of filaments and halos, dense regions connected by long, thin bridges, like a cosmic spider's web, and the ordinary gas began falling into those dark matter halos, pooling at the centres, compressing, heating up. And eventually in the densest pockets the gas got hot enough and dense enough to ignite nuclear fusion. The first stars were born. When exactly this happened is one of the great uncertainties. The standard estimate places the formation of the very first stars somewhere around 100 to 250 million years after the Big Bang during the tail end of the Dark Ages. These first stars, called Population 3 stars, have never been directly observed. They are theoretical ghosts, predicted by simulations but never seen. They were probably enormous, hundreds of times the mass of the Sun, burning through their fuel in just a few million years before exploding as supernovae, seeding the surrounding gas with the first heavy elements, carbon, oxygen, silicon, iron, the raw materials for planets, for chemistry, for eventually you. And then, slowly, over the next several 100 million years, the first proto-galaxies began to assemble. Small clumps of stars and gas, merging with other small clumps, growing gradually, hierarchically, like companies merging into corporations. The standard model predicted that by 300 million years after the Big Bang, you might see a few dim, tiny collections of stars, hardly deserving of the word galaxy, still in the earlier stages of assembly. Nothing massive, nothing luminous. Nothing that would show up as a bright, well-defined object in even the most powerful telescope. Scholars still argue whether the standard timeline was always understood to be approximate, or whether it had calcified into something more rigid, a set of expectations that had gone unchallenged for so long that they started to feel like facts. Either way, when JWST pointed its mirror at the deep sky and saw what was actually there at 300 million years, the timeline did not just need adjusting. It needed, in the careful words of one widely circulated paper, significant revision. You're breathing through that timeline now, in and out, each breath 100 million years, and the Dark Ages feel appropriately cozy. The Dark Ages are ending now, at least in the story, and the first faint light is beginning to kindle in the void around you. Tiny, fierce, blue-white pinpricks, the earlier stars burning through their hydrogen fuel with reckless intensity, living fast and dying spectacularly. But stars alone do not make a galaxy. A galaxy requires architecture. It requires a gravitational framework, a reservoir of gas, a sustained process of star formation, and most importantly, it requires time. Or at least, that is what everyone thought. To understand why JWST 130 is such an affront to theoretical astrophysics, you need to understand how galaxies were supposed to come together, piece by painstaking piece, in the standard model of cosmic structure formation. The model is called hierarchical assembly, and it is elegant in the way that slow, patient things are often elegant. Think of it like building a city. You do not wake up one morning and find a metropolis where yesterday there was only farmland. First, someone builds a house. Then a few more houses cluster together into a hamlet. Hamlets merge into villages. Villages grow into towns. Towns absorb surrounding settlements and become cities. Cities sprawl into metropolitan areas. Each stage takes time, and each stage depends on the previous one being complete. You cannot skip steps. You cannot go from scattered farmhouses to a skyline of glass towers overnight. The raw materials have to be gathered, the infrastructure has to be laid, the population has to grow. It is sequential, it is hierarchical, it is above all slow. In the cosmic version of this story, the first structures to form are small dark matter halos, clumps of invisible matter that condensed out of the tiny density fluctuations in the early universe. These halos are modest, perhaps a few million solar masses, and they attract ordinary gas into their gravitational wells. The gas cools, contracts, and forms the first small clusters of stars. These mini halos then begin to merge with each other, drawn together by gravity, combining their stars and gas into larger systems. Those larger systems merge with other systems, and so on in a nested cascade of gravitational acquisitions that spans billions of years. The Milky Way itself is thought to have assembled through dozens, perhaps hundreds, of such mergers over the course of cosmic history. It is still merging today, in fact, slowly devouring several smaller satellite galaxies, including the Sagittarius Dwarf Elliptical Galaxy, which is being gravitationally shredded as you lie here breathing. The key prediction of hierarchical assembly is that at very early times you should see only the smallest building blocks. The little halos, the mini clusters, the galactic equivalents of mud huts and campfires. Large, massive, luminous galaxies should not appear until much later, because they require many generations of mergers to assemble. A galaxy with a stellar mass of 1 billion solar masses in the standard picture needs at least 1 billion years of merging and star formation to reach that size. Some models push the estimate even higher. The universe at 300 million years simply has not had enough time for the hierarchical process to produce anything that large. It would be like expecting a cathedral to exist in a civilization that invented the brick last Tuesday. And yet the simulations were confident, enormously, reassuringly confident. Over the past 2 decades, cosmologists have built increasingly sophisticated computer simulations of cosmic structure formation, programs with names like Illustris, Eagle, and Illustris TNG that model the gravitational interactions of billions of virtual particles, track the flow of gas, account for the feedback from supernovae and black holes, and produce stunningly realistic virtual universes. When you compare these simulated universes to the real one, the agreement is remarkable. The large-scale structure, the cosmic web of filaments and voids that galaxies trace across the sky, matches beautifully. The distribution of galaxy masses at low redshifts matches. The properties of galaxy clusters match. The simulations were so successful that they bred a kind of theoretical complacency, a quiet confidence that the basic framework was correct, and that any remaining discrepancies were just details to be ironed out. There is a quirky footnote to this confidence that is worth mentioning. One of the earliest large-scale cosmological simulations, called the Millennium Simulation, was run in 2005 using roughly 10 billion virtual particles. At the time, it was the most computationally expensive simulation of its kind ever performed, requiring about a month of continuous processing on one of Germany's most powerful supercomputers. Today, a comparable simulation could be run on a high-end gaming computer in a fraction of the time. The exponential growth of computing power has been a gift to cosmology, but it has also meant that each generation of simulations inherits the assumptions of the previous generation, refined but rarely questioned at the foundational level. And the foundational assumption, the one that JWST would soon challenge, was that star formation in the early universe was inefficient. The reasoning made sense. Early gas was pristine, lacking the heavy elements that help gas cool and condense efficiently. Without efficient cooling, gas clouds could not fragment into the dense cores needed to form stars at a high rate. Supernovae and energetic radiation from the first stars would heat and disperse surrounding gas, further slowing the process. Feedback, the astronomers called it. Negative feedback. The first stars, by their very existence, made it harder for the next generation of stars to form. It was a self-regulating system, a cosmic thermostat, and it kept early galaxies small, dim, and manageable. Scholars still argue whether this assumption of low star formation efficiency was truly demanded by the physics, or whether it was partly a convenience, a simplification that made the simulations tractable and happened to produce results that matched the limited observational data available at the time. Hubble could not see deeply enough to test the prediction directly. The earliest galaxies were beyond its reach, hiding in the infrared dark, so the models stood, elegant and unchallenged, like a theory of architecture developed by people who had never actually visited a construction site. And then someone handed them a telescope that could see the construction site, and what they found there was not mud huts. What they found was a mansion. Maybe not a mansion by the standards of the modern universe, where galaxies like the Milky Way contain hundreds of billions of stars and span 100,000 light-years from rim to rim. But by the standards of a universe barely 300 million years old, JD's GSE 13.0 was outrageously, almost offensively large. You're still lying there in the dark, and you can let this image form slowly behind your closed eyes. A dense, compact knot of stars blazing with ultraviolet light, surrounded by a halo of gas that is still falling inward, still feeding the furnace. The whole thing is small by galactic standards, maybe a few thousand light-years across, but it is packed. Stars are forming at a furious rate, far faster than anything the simulations predicted for this epoch. The stellar mass, as estimated from the brightness and colour of the light JWST detected, is somewhere in the range of several 100 million solar masses, with some analyses pushing it even higher. Let that sink into your pillow for a moment. Several 100 million solar masses worth of stars. Each solar mass is the mass of our Sun, which is itself about 330,000 times the mass of Earth. So you're talking about a quantity of stellar material so vast that expressing it in any unit smaller than solar masses becomes absurd. And all of that material has not only been gathered together, but has already been processed through nuclear fusion in the cores of stars, meaning those stars had to form, live, and in many cases die before the epoch at which JWST is observing. The stars you're seeing are not the first generation. They cannot be. The spectral signatures suggest the presence of heavy elements, which means at least one prior generation of stars must have lived, fused hydrogen and helium into heavier elements, exploded, and enriched the surrounding gas, which then cooled, collapsed, and formed the stars you are now detecting. That is at least 2 full stellar generations crammed into 300 million years. Now, 300 million years is not nothing. A massive star can burn through its entire life cycle in just a few million years, so in principle, you could fit dozens of stellar generations into that time frame. The problem is not the stars themselves. The problem is everything else. The gas has to collect, the dark matter halo has to form, the gas has to cool, the first stars have to ignite, live, die, and disperse their heavy elements. That enriched gas has to cool again, collapse again, and form new stars. And all of this has to happen not in a tiny isolated pocket, but across a region large enough to accumulate hundreds of millions of solar masses of stellar material. The logistics are staggering. It is like planning a wedding, a house renovation, and a cross-country move simultaneously, except each task depends on the previous one being finished, and you have a deadline that the laws of physics set and cannot extend. The standard models had run these logistics countless times. They knew how fast dark matter halos could grow through mergers. They knew how quickly gas could cool and condense. They knew how much energy supernovae injected back into the surrounding medium, slowing subsequent star formation. And when they put all of those ingredients together and asked, what is the most massive galaxy you could plausibly build in 300 million years? The answer came back consistently. Not this massive, not even close. The models predicted that the most massive galaxies at redshift 13 should have stellar masses of perhaps a few million solar masses. JWST-GS-Z13-0 exceeded that prediction by a factor of roughly 100. A factor of 100 is not a minor discrepancy. A factor of 100 is not a rounding error. A factor of 100 is the difference between a paper airplane and a Boeing 747. It is the kind of discrepancy that makes theorists go very quiet and then very loud in rapid succession. There is a historical parallel that might amuse you as you drift. In 1859, the French mathematician Urbain Le Verrier noticed that the orbit of Mercury deviated slightly from the predictions of Newtonian gravity. The discrepancy was tiny, just 43 arc-seconds per century, but it was persistent and unexplained. For decades, astronomers tried to patch Newtonian theory to account for it, proposing hidden planets, dust clouds, even a slight ablateness of the sun. None of the patches worked. It took Einstein's general theory of relativity in 1915 to finally explain Mercury's orbit, and in doing so, it replaced the entire gravitational framework. Sometimes a small discrepancy points to a small error. Sometimes it points to a revolution. Scholars still argue about which category JWST's impossible galaxies fall into, and the debate is far from settled. But the sheer scale of the mismatch between prediction and observation was hard to dismiss. This was not 43 arc-seconds. This was a galaxy that was 100 times more massive than it should have been, sitting at an epoch where the standard model said nothing remotely like it could exist. And the most unsettling part, the part that kept astronomers awake at night even as you drift closer to sleep, was the nagging suspicion that JD's GSZ13-0 might not be an outlier. It might not be a freak, a 1 in a billion statistical anomaly that just happened to fall in JWST's field of view. Because as the data kept coming in, as more survey fields were processed and more high redshift candidates were identified, it became increasingly clear that the universe at early times was not just slightly busier than expected. It was dramatically, systematically, almost gleefully busier. The galaxy that should not exist, it turned out, had company. You feel the faintest smile tugging at the edges of your drowsiness, because there is something undeniably entertaining about the universe refusing to behave. The company arrived quickly, and it arrived in numbers that made the theorists reach for stronger coffee. You're floating again, drifting through the deep survey fields that JWST spent its first year meticulously observing and all around you, like fireflies waking in a summer meadow, the impossible galaxies are appearing. Not one, not two, dozens. Each one a smudge of ancient infrared light, each one sitting at a redshift that placed it in the first few 100 million years of cosmic history. Each one far too massive, far too bright, or far too structured to fit comfortably within the standard model of galaxy formation. JWST 13.0 had cracked the door open. What followed was a flood. One of the first to make headlines alongside it was GNZ 11, a galaxy that had actually been discovered by Hubble back in 2016 and held the record for the most distant known galaxy for several years. Hubble had measured its redshift photometrically at around 11, placing it roughly 400 million years after the Big Bang. But Hubble's data was limited, and there was always a whisper of uncertainty about whether the redshift was real. JWST settled the question definitively with spectroscopic confirmation, pinning the redshift at 10.6 and revealing that GN-Z11 was not just distant but genuinely strange. It was compact, incredibly luminous, and appeared to harbour an active galactic nucleus, meaning a supermassive black hole at its centre was actively devouring material and releasing enormous amounts of energy. A supermassive black hole in a galaxy that existed when the universe was barely 400 million years old. That was its own separate crisis, but we'll get to the black holes later. For now, just note that GNZ11 was bright, massive, and far too precocious for the standard model's comfort. Then there was CEERS 93316, a candidate identified in the Cosmic Evolution Early Release Science Survey at a photometric redshift that initially appeared to be around 16.7. If confirmed, that would have placed it at roughly 250 million years after the Big Bang, shattering every existing distance record. The internet erupted, press releases were issued, breathless articles were written, and then, as spectroscopic follow-up data came in, the redshift was revised downward to about 4.9, making it a much closer and far less exciting galaxy that had been masquerading as a record breaker due to a quirk of its photometric colours. The incident was a useful reminder that photometric redshifts, while powerful, are not infallible. But it also illustrated the frenzied atmosphere of those early months, when every new data release felt like it might contain the next paradigm-shifting discovery, and astronomers were racing to publish before their competitors could scoop them. Not all the candidates deflated so dramatically, though. The GLASS Early Release Science program found several robust high redshift galaxy candidates, two of which appeared to sit at redshift of 10 to 12 with stellar masses that strained the models. The Cosmos Webb Survey, one of JWST's largest observing programs, began turning up massive galaxy candidates at redshifts between 7 and 10 that were simply too numerous to explain as statistical flukes. And then, in February 2023, a paper landed that sent the cosmology community into something resembling a polite panic. The paper, authored by a team led by Ivo Labbé at Swinburne University of Technology in Australia, reported the discovery of 6 massive galaxy candidates at redshifts between 7 and 9, corresponding to ages of roughly 500 to 700 million years after the Big Bang. The galaxies were not just massive, they were extraordinarily massive, with estimated stellar masses comparable to, or even exceeding that of the present-day Milky Way. The Milky Way, a galaxy that has had 13.8 billion years to assemble its stars. And these objects appeared to have reached a similar mass in less than 1 billion years. The paper's title was restrained, as academic titles tend to be, but the media dubbed these objects universe breakers, and the name stuck because it captured something real about the emotional and intellectual impact of the discovery. There is a delightful quirk to how the Universe Breakers paper was received. Within days of its posting on the preprint server, it had been downloaded tens of thousands of times, a staggering number for an astrophysics paper. Normally, a well-received paper in the field might accumulate a few hundred downloads in its first week. The Universe Breakers got more downloads in 48 hours than most papers get in a year. Astrophysicists who had never appeared on mainstream news found themselves fielding calls from CNN and the BBC. One researcher joked on social media that they had spent 20 years studying galaxy evolution in quiet obscurity and were now being asked to explain the end of cosmology to morning television hosts who could not pronounce photometric. Scholars still argue whether the term Universe Breakers was helpful or harmful to public understanding. On one hand, it conveyed the genuine magnitude of the surprise. On the other, it implied that the universe itself was somehow broken, when really it was the models that were struggling. The universe was doing exactly what it had always done. It was just doing it faster than anyone had expected. The galaxies were not breaking the universe. They were breaking the story we had told ourselves about the universe, which is a different thing entirely, though it can feel just as disorienting. You're surrounded by them now in your imagination, these ancient rebel galaxies glowing stubbornly in the infrared dark, each one a challenge, each one a question mark. And the questions they posed were not abstract or academic. They cut to the very foundations of how we understand the first billion years of cosmic history. Were the models wrong? Were the observations wrong? Was there some exotic new physics lurking in the early universe that nobody had accounted for? The scramble for answers was already underway, and it was messy, contentious, and utterly fascinating. Your breathing is slow and steady, like the expansion of space itself, and the fireflies of ancient light pulse gently around you. The scramble looked exactly the way you might expect a scientific crisis to look, which is to say, it looked a lot like a very intense group chat that had spilled out into the real world. You're lying still, the impossible galaxies hovering in your peripheral vision like questions that refuse to dissolve, and now you get to watch the astronomers react. It was not a single coordinated response. It was dozens of individual responses, overlapping, contradicting, reinforcing, and occasionally sniping at each other across the pages of preprint servers and the character limits of social media posts. The first months after JWST's initial data release were, by the standards of a normally sedate academic field, absolutely chaotic. The preprint server archive, where physicists and astronomers post their papers before formal peer review, saw a torrent of submissions in the second half of 2022 and the first months of 2023. Papers with titles that range from cautiously technical to borderline theatrical. The impossibly early galaxy problem. A new crisis in cosmology. Are high redshift galaxies consistent with lambda CDM? Each one grappling with the same fundamental question: how do you reconcile what JWST was seeing with what the standard cosmological model predicted it should see? The answer, depending on which paper you read, range from "you don't, and that's exciting," to "calm down, the data might be wrong," to "here's a speculative new theory I came up with last weekend." The social media dimension was something genuinely new. Previous cosmological upheavals had played out in journals, at conferences, and in private correspondence. The discovery of the accelerating expansion of the universe in 1998, for instance, was a slow burn, debated intensely within the community before gradually reaching the public. But JWST's impossible galaxies erupted in real time on Twitter, where astronomers with large followings posted their reactions, their analyses, and occasionally their existential crises for hundreds of thousands of followers to watch. One widely shared thread by an astrophysicist at a major American university began with the words, "I think I need to sit down," and proceeded to walk through the implications of the Labe paper in language accessible enough that it was retweeted by celebrities and politicians who had probably never thought about redshift before in their lives. There was excitement, certainly, the frisson of genuine discovery, the sense that something important was happening, that the textbooks might need rewriting. But there was also anxiety, particularly among theorists who had built their careers on the standard model of galaxy formation. If the models were fundamentally wrong about the early universe, then decades of work on simulations, on feedback prescriptions, on merger trees was potentially compromised. Not worthless, not necessarily, but certainly less reliable than everyone had assumed. The stakes were professional as well as intellectual, and that combination tends to produce strong emotions even in people who pride themselves on dispassionate rationality. A few prominent voices counselled patience. One senior astronomer, in an interview that was widely circulated, compared the situation to the early days of the Hubble Space Telescope, when Hubble's initial data on the expansion rate of the universe appeared to conflict with estimates from other methods. The discrepancy caused years of heated debate before improvements in calibration and analysis brought the measurements into closer agreement. The lesson, this astronomer argued, was that new telescopes always produce surprising initial results, and the first interpretation is rarely the final one. Give the data time to mature. Let the calibrations settle. Do not rewrite cosmology based on photometric redshifts that have not been spectroscopically confirmed. Others were less patient. A group of theorists published a paper within weeks of the Labe universe breaker's announcement, arguing that if even one of those 6 galaxies was confirmed at its estimated mass and redshift, the lambda CDM model would face a challenge more severe than any it had encountered in its 3-decade history. The paper used statistical language, but the subtext was unmistakable. Something might be seriously wrong, and pretending otherwise in the name of caution was itself a form of bias. There is a quirky detail from this period that captures the mood perfectly. A cosmologist in Europe created a website, a simple single-page site with a dark background that tracked the number of JWST papers posted to AskWar that used the word tension in their titles or abstracts. Tension is the diplomatic term astronomers use when observations and theory disagree. It is softer than contradiction and more collegial than your model is broken. Within 6 months of JWST's first data release, the counter on that website had passed 200. 200 papers, each one documenting a tension, a discrepancy, a raised eyebrow. The website became a minor meme in the astrophysics community, shared with a mixture of amusement and unease, and through it all, JWST kept observing. The telescope did not care about the arguments. It did not read the preprints or check Twitter. It sat at the second Lagrange point, its golden mirror facing the void, its instruments cooled to near absolute zero, patiently collecting photons that had been travelling for billions of years. Every few weeks a new batch of data was downlinked to Earth, processed, calibrated, and released to the science teams. And every few weeks, the pile of impossible galaxies grew a little larger. Scholars still argue whether the speed of the response, the rush to publish, the social media amplification, the headline-grabbing language, was beneficial or detrimental to the scientific process. Some argue it accelerated progress, forcing rapid iteration and public accountability. Others worry it incentivized premature conclusions and created a media narrative that outpaced the actual evidence. The truth, as is usually the case, probably lies somewhere in the uncomfortable middle. But one thing was beyond dispute. The astronomical community had not experienced this level of collective agitation since the discovery of dark energy, and that discovery had won its authors a Nobel Prize. You turn your head slightly on the pillow, and the faint hum of debate seems to fade, replaced by the quiet patience of a golden mirror collecting ancient light, one photon at a time. But what if they were wrong? Not the theorists this time, but the observers. What if the data itself was the problem? You're sinking deeper into the mattress, and this is the part of the story where the mood shifts from exhilaration to something more measured, more cautious, like a detective returning to the crime scene a second time with better lighting and a magnifying glass. Because in the rush of those early months, amid the breathless headlines and the frantic preprints, a quieter group of astronomers was raising a hand and saying, politely but firmly, that perhaps everyone should slow down. The concern was not frivolous. It was rooted in a genuine understanding of how tricky it is to extract reliable measurements from the faintest, most distant objects in the universe. Remember that most of the early JWST discoveries were based on photometric redshifts, the technique where you photograph a galaxy through several filters and infer its distance from the pattern of brightness across those filters. Photometric redshifts are fast. They can be applied to hundreds or thousands of objects simultaneously. But they are also susceptible to a particular kind of error that astronomers call a catastrophic outlier, which is a wonderfully dramatic name for what is essentially a case of mistaken identity. Here is how it works. A galaxy at very high redshift has a characteristic signature in its photometric data. The light at wavelengths shorter than a certain cutoff is almost completely absorbed by neutral hydrogen in the intergalactic medium, creating a sharp drop in brightness called the Lyman break. The position of this break shifts to longer wavelengths as the redshift increases, so by identifying where the break falls across your filter set, you can estimate the redshift. The problem is that other things can mimic this signature. A dusty galaxy at a much lower redshift can appear very red, with a steep drop in brightness at shorter wavelengths, and in a limited set of filters, it can look almost identical to a genuine high redshift object. A galaxy with an unusual stellar population, very old stars for instance, or stars with peculiar chemical compositions, can also produce confusing photometric colours. The result is that some fraction of your high redshift candidates will turn out to be imposters, closer galaxies in disguise. This was not a hypothetical concern. Remember CEE RS 93316, the galaxy that initially appeared to be at a record-shattering redshift of 16.7. When spectroscopic data came in, it turned out to be at a redshift of about 4.9, a perfectly ordinary galaxy that had fooled the photometric analysis. If one high-profile candidate could be that wrong, skeptics argued, how many others in the growing catalogue of impossible galaxies might also be misidentified? There were other potential sources of error as well. JWST's instruments, while extraordinarily sensitive, were brand new. Their calibration was still being refined. The process of converting raw detector readings into calibrated flux measurements, how bright an object actually is at each wavelength, depends on a detailed understanding of how the instruments respond, and that understanding improves over time as more calibration data is collected. In the very first months of operation, some calibration uncertainties were significant enough to affect photometric redshift estimates and, more critically, stellar mass estimates. If you overestimate how bright a galaxy is because your calibration is slightly off, you will overestimate its stellar mass, and a galaxy that seemed impossibly massive might turn out to be merely surprisingly massive, which is a very different category of problem. Several teams published papers in late 2022 and early 2023 specifically addressing these calibration issues. One widely discussed paper showed that updated calibrations reduced the estimated stellar masses of some high redshift candidates by factors of 2 to 5. That was significant. A galaxy that initially appeared to have a stellar mass of 10 billion solar masses might actually have a mass of 2 billion, which is still large for its epoch but considerably less universe-breaking. Another paper demonstrated that the choice of stellar population model, the theoretical template used to convert observed light into physical properties like mass and age, could shift the results substantially. Different models built on different assumptions about star formation history, dust content and metallicity could yield stellar mass estimates that varied by an order of magnitude for the same observed data. There is an analogy that might help you feel this uncertainty rather than just understand it. Imagine you are trying to estimate the weight of a person standing on the far side of a foggy field. You can see their silhouette roughly. You can tell they are not a child and not a giant. But depending on what assumptions you make about their build, their clothing, whether they're carrying a backpack, your estimate might range from 50 kilograms to 150. You're not wrong to make an estimate. You're just working with limited information, and the error bars are wide. That is essentially where the early JWST mass estimates lived, in a fog of uncertainty that was real and acknowledged by the observers themselves, even as the headlines focused on the most dramatic numbers. Scholars still argue whether the caution was proportionate or excessive. The skeptics were performing an essential function, stress testing the observations, demanding rigour, preventing the field from stampeding toward premature conclusions. But some of the bolder observers felt that the skeptics were applying an unfairly high bar of evidence to results that challenged the standard model, while accepting far less scrutiny for results that confirmed it. This is a recurring dynamic in science, a kind of asymmetric skepticism where extraordinary claims are held to extraordinary standards, while ordinary claims slip through with minimal examination. Whether that asymmetry is a feature or a bug of the scientific method is itself a matter of debate, and not one that was going to be resolved on Twitter. What everyone agreed on, though, was that the definitive answer would come from spectroscopy. Not photometric guesses, not statistical arguments, but hard spectroscopic confirmation. Point the telescope at these candidates, spread their light into a full spectrum, and look for the unmistakable fingerprints of specific chemical elements shifted to precisely measurable wavelengths. That would settle it. Your eyelids flutter, barely, and the fog on the field thins just slightly. The spectra came, and the fog did not just thin, it parted. You're lying very still now, you're breathing slow and rhythmic, and somewhere in the dark above you the golden mirror is doing its most painstaking work. Spectroscopy is not fast. It is not the quick snapshot of photometric imaging, where you can photograph thousands of galaxies in a single exposure. Spectroscopy requires you to focus on individual objects, one at a time or a few at a time, and collect their light for hours, spreading it into a rainbow of wavelengths and searching for the faint emission lines that reveal a galaxy's true distance and chemical composition. It is the difference between glancing at a crowd and sitting down with one person for a long conversation. It takes time, it takes patience, but when it works, it is definitive. JWST carried an instrument perfectly suited for this task. The Near-Infrared Spectrograph, or NIR spec, was designed to capture spectra of extremely faint objects in the infrared, and it had a remarkable capability called multi-object spectroscopy, which allowed it to observe up to 200 objects simultaneously using a grid of tiny configurable shutters, each one opening or closing to admit light from a specific target while blocking everything else. It was like having 200 tiny windows, each one pointed at a different galaxy, all collecting data at the same time. This made NIRSpec extraordinarily efficient, and the JADES team used it aggressively, targeting their most promising high redshift candidates for deep spectroscopic follow-up. The results began appearing in late 2022 and accelerated through 2023, and they were, for the most part, devastating to the skeptics' hopes that the problem would simply go away. Galaxy after galaxy had its photometric redshift confirmed spectroscopically. JWST 13.0 was confirmed at a redshift of 13.2, placing it firmly at around 320 million years after the Big Bang. Another object, JWST 12-Z was confirmed at a redshift of 12.6. GN-Z11, the Hubble-era record holder, was spectroscopically confirmed and revealed to have even more peculiar properties than previously thought, including signatures of highly ionized nitrogen that suggested extreme conditions in its core. One by one, the candidates were being validated. The imposter fractions, the number of objects whose photometric redshifts turned out to be wildly wrong, was real but modest. Some candidates did drop to lower redshifts. Some turned out to be dusty interlopers at more moderate distances. But the overall population of genuinely early, genuinely massive galaxies survived the spectroscopic gauntlet with its essential character intact. There was a particular moment, widely discussed in the community, when the JWST team presented a spectroscopic confirmation of a galaxy at redshift 14.3, which, if accurate, would place it at barely 290 million years after the Big Bang. The announcement was made at a major astronomical conference, and attendees described the room as simultaneously thrilled and uneasy, the way you might feel watching a tightrope walker who is clearly talented but is performing without a net over a very deep canyon. A redshift of 14.3 was not just high, it was in territory where the universe was still in the process of reionization, the epoch when the first stars and galaxies produced enough ultraviolet radiation to ionize the neutral hydrogen that filled intergalactic space. Finding a substantial galaxy in the middle of this process was like finding a fully furnished apartment in a building that was still under construction, and the spectra revealed more than just distances. They revealed chemistry. The emission lines that a NEOSPEC detected told astronomers what elements were present in these galaxies and in what proportions. Several of the confirmed high redshift galaxies showed clear signatures of oxygen, which is an element that can only be produced by nuclear fusion in massive stars and dispersed by supernova explosions. The presence of oxygen at these early epochs meant that at least one full generation of massive stars had already lived and died before the light JWST was detecting had been emitted. This was consistent with the two-generation scenario suggested by the photometric data, but now confirmed by direct chemical evidence. The stellar populations in these galaxies were not entirely primordial. They had already been enriched by the deaths of earlier stars. There is a historical fact tucked into this that is easy to overlook but worth savouring. The element oxygen, which makes up about 65% of your body mass, and which you're breathing in and out right now as you listen, did not exist in the early universe, not a single atom of it. Every oxygen atom in existence was forged inside a star, and the detection of oxygen at redshift 13 means that the alchemical machinery of stellar nucleosynthesis was already running at full capacity when the universe was barely old enough to have stars at all. You are, in a very real sense, made of a substance that these impossibly early galaxies were already manufacturing. Scholars still argue about the precise implications of the spectroscopic confirmations. The masses were still uncertain because spectroscopy tells you distance and chemistry, but does not directly measure stellar mass. You still need to model the stellar populations to infer mass from the observed luminosity, and those models still carry significant uncertainties. Some researchers pointed out that the confirmed galaxies, while genuinely distant, might still have lower masses than the initial photometric estimates suggested. Others countered that even the revised lower masses were still uncomfortably high for the standard model. The conversation had shifted from "are these galaxies real?" to "how bad is the problem exactly?", which was progress of a sort but not the kind that let anyone relax. You're breathing oxygen that was forged in stars, and somewhere in the ancient universe, galaxies that should not exist were already making more of it. the spectra do not lie. The lines are where they are, the chemistry is what it is, and the fog, for better or worse, has lifted. You breathe in, and the oxygen fills your lungs, and now you need to think about something you cannot see, something that makes up roughly 85% of all the matter in the universe, and yet has never been directly detected by any instrument ever built. Something that does not glow, does not absorb light, does not bounce off anything, does not interact with electromagnetism in any way whatsoever. It is there, though. You know it is there because without it, nothing in the universe makes gravitational sense. Galaxies spin too fast. Galaxy clusters are too heavy. The cosmic microwave background has the wrong pattern of ripples. Without this invisible substance holding everything together, the entire architecture of the cosmos falls apart like a house built without nails. You're thinking about dark matter, and dark matter is where the story of the impossible galaxies gets even stranger. In the standard model of structure formation, dark matter is the architect. It is the scaffolding upon which everything visible is built. Because dark matter interacts only through gravity, it began clumping much earlier than ordinary matter, which was stuck in the hot plasma of the early universe and could not collapse until after recombination. By the time ordinary matter was freed, around 380,000 years after the Big Bang, dark matter had already been quietly assembling itself into a cosmic web of halos and filaments. These dark matter halos are the gravitational cradles into which ordinary gas falls, cools, and eventually forms stars. No halo, no galaxy. It is that simple. Every galaxy you have ever seen in a photograph, every spiral and elliptical and irregular smudge of light, sits at the center of a dark matter halo that is vastly larger and more massive than the visible galaxy itself. The Milky Way's dark matter halo extends far beyond the visible disk of stars, forming an enormous invisible sphere roughly 10 times the diameter of the galaxy you can actually see. The size and growth rate of dark matter halos are among the most precisely modelled quantities in cosmology. Simulations track billions of dark matter particles as they gravitationally attract one another, merge, and build up structures over cosmic time. The results are remarkably consistent across different simulation codes and different research groups. At very early times, the halos are small. They grow through mergers, absorbing smaller halos, gradually building up mass. The rate of growth is governed by the density of the universe, the expansion rate, and the statistical properties of the initial density fluctuations, all of which are tightly constrained by observations of the cosmic microwave background. This means that the maximum mass a dark matter halo can reach at any given epoch is not a free parameter. It is a prediction, and a fairly firm one. And here is where the impossible galaxies create a problem that goes deeper than just star formation efficiency. If JD's GSZ 13-0 has a stellar mass of several hundred million solar masses, then the dark matter halo hosting it must be considerably more massive still, because only a fraction of a halo's baryonic matter, the ordinary stuff, the gas and stars, actually ends up in stars. In the local universe, this fraction, called the star formation efficiency, is typically around 10 to 20% for halos of a certain mass range, and it drops sharply for both smaller and larger halos due to various feedback mechanisms. So if you observe a galaxy with a stellar mass of 500 million solar masses, and you assume a generous star formation efficiency of 20%, the total baryonic mass in that halo is at least 2.5 billion solar masses, and the dark matter halo itself must be roughly 10 times that, placing it in the range of 25 billion solar masses or more. Now ask the simulations whether a dark matter halo of 25 billion solar masses can exist at redshift 13. The answer you get back is technically yes, but only barely. Such halos correspond to the extreme tail of the statistical distribution, the rarest of the rare, the kind of objects you might expect to find one or two of in the entire observable universe at that epoch. Finding even one in the relatively small survey area of JDs would be statistically improbable. Finding several, across multiple surveys, begins to look less like bad luck and more like a systematic failure of the model. There is a quirky thought experiment that cosmologists sometimes use to illustrate this. Imagine you have a bag containing 1,000,000 marbles, 999,000 of which are blue, and 1,000 of which are red. If you reach in and pull out one red marble, you might shrug. Unlikely, but not impossible. If you pull out 10 red marbles in a row, you start to suspect the bag is not what you were told it was. The impossible galaxies are the red marbles, and JWST keeps pulling them out. Some theorists responded by proposing that dark matter itself might behave differently in the early universe than the standard model assumes. Most cosmological simulations use cold dark matter, meaning dark matter particles that move slowly and clump efficiently on small scales. But what if dark matter has properties that enhance early structure formation? What if dark matter particles can interact with each other in subtle ways that standard cold dark matter does not allow? What if there is a component of warm dark matter, particles that move faster and smooth out small-scale structure, but might somehow promote the growth of the largest halos through mechanisms not yet fully understood? These ideas were speculative, and most theorists treated them as last resorts rather than first explanations. But the fact that they were being discussed at all told you something about the severity of the problem. Scholars still argue whether the dark matter halo issue is truly independent of the star formation efficiency issue, or whether the two are entangled in ways that make the problem look worse than it actually is. If early star formation was much more efficient than assumed, then the required halo masses drop, and the tension with dark matter predictions eases. But making star formation more efficient has its own costs and complications, and you will hear about those soon enough. The invisible scaffolding holds for now, but it is creaking. The scaffolding creaks a little louder when you notice what is sitting at the centre of some of these early galaxies. Not just stars, not just gas. Something far more violent, far more concentrated, far more difficult to explain. You're drifting in the dark, half asleep, and now there is a monster in the room. A quiet one, invisible except for the havoc it wreaks on everything that falls too close, but a monster nonetheless. You're thinking about supermassive black holes, and JWST found them in places where they had absolutely no business being. Black holes themselves are not controversial. Stellar mass black holes, the kind that form when a massive star collapses at the end of its life, are a well-understood prediction of general relativity, confirmed by gravitational wave detections and X-ray observations of binary systems. They typically weigh between a few and a few dozen solar masses. Supermassive black holes are a different beast entirely. These are objects weighing millions to billions of solar masses, sitting at the centres of most large galaxies, including our own Milky Way, which harbours a supermassive black hole called Sagittarius A star, with a mass of about 4 million suns. Supermassive black holes are not formed by the collapse of a single star. They're too large for that. They must have grown over time, accreting gas, swallowing smaller black holes, building up mass through a sustained process of gravitational feeding. The problem, much like the problem with the impossible galaxies, is time. A black hole can only accrete matter so fast. There is a theoretical limit, called the Eddington limit, which describes the maximum rate at which material can fall into a black hole before the radiation pressure from the infalling material pushes back hard enough to halt the flow. It is like trying to pour water into a funnel. If you pour too fast, the water backs up and spills over. A black hole feeding at the Eddington limit can roughly double its mass every few tens of millions of years, depending on its size and the properties of the surrounding gas. Starting from a stellar mass seed, say 100 solar masses, the remnant of a massive first-generation star, and growing at the maximum possible rate, it takes at least several hundred million years to reach 1 million solar masses and considerably longer to reach 1 billion. So when JWST found evidence of supermassive black holes in galaxies at redshifts of 8, 9, 10 and beyond, the question was immediate and uncomfortable. How did they get so big so fast? At redshift 10, the universe is about 500 million years old. Even if a seed black hole formed from one of the very first stars at perhaps 100 to 200 million years after the Big Bang, that leaves only 300 million years of growth. 300 million years at the Eddington limit starting from a stellar mass seed gets you to maybe 1 million solar masses if you are generous with the assumptions. But some of the black holes JWST detected appeared to weigh tens of millions of solar masses or more. The math simply does not work unless something unusual happened. GNZ 11, that bright compact galaxy at redshift 10.6 that we encountered earlier, showed spectroscopic signatures consistent with an active galactic nucleus powered by a substantial black hole. Other high redshift objects found in the JADES and SEERS surveys showed similar signs. One particularly striking discovery, announced in 2023, involved a black hole estimated at roughly 10 million solar masses in a galaxy at redshift 8.7, corresponding to an age of about 600 million years. The black hole was not just present, it was actively feeding, producing radiation that could be detected across billions of light years, and it accounted for a suspiciously large fraction of the galaxy's total mass. In the local universe, supermassive black holes typically represent about 0.1% of their host galaxy's stellar mass. This early black hole appeared to constitute several percent, suggesting that the black hole and the galaxy had grown up together in an unusual, perhaps unprecedented relationship. The proposed solutions were creative and sometimes exotic. One idea was that the seed black holes were simply larger than stellar remnants. Instead of forming from the collapse of individual massive stars, perhaps the first black holes formed from the direct collapse of enormous gas clouds, skipping the star stage entirely and producing seeds of 10,000 to 100,000 solar masses right from the start. These direct collapse black holes, as they are called, have been theorized for years but never observed. They require very specific conditions: pristine gas with no heavy elements, intense ultraviolet radiation to prevent the gas from fragmenting into stars, and a dark matter halo of just the right mass. Whether these conditions were common enough in the early universe to produce a significant population of massive seeds is a matter of active debate. Another idea was that early black holes could exceed the Eddington limit for sustained periods, a process called super-Eddington accretion. If the geometry of the infalling gas is right, if the material approaches in a thick disk or through narrow funnels that allow radiation to escape sideways without impeding the inflow, then the effective accretion rate could be several times higher than the classical Eddington limit. This would allow faster growth, but modelling super-Eddington accretion is notoriously difficult, and whether it can be sustained for long enough to explain the observed black hole masses is uncertain. Scholars still argue whether the supermassive black hole problem is fundamentally separate from the impossible galaxy problem, or whether they are two symptoms of the same underlying disease. A universe that was far more efficient at concentrating and processing matter in its first billion years than any existing model anticipated. There is a historical echo here worth noting. When quasars were first discovered in the early 1960s, their enormous luminosities at great distances baffled astronomers for years. The eventual explanation, supermassive black holes powering relativistic jets, seemed outlandish at the time but is now textbook. Perhaps the early universe's black holes will follow a similar arc, from impossible to inevitable. You feel the gravity of the idea pulling gently at the edges of your thoughts, Not enough to wake you, just enough to deepen the drift. The gravity deepens, and now the conversation shifts from what went wrong with the models to what might fix them. You are nestled in the dark, and the theorists around you, imagine them as faint murmuring shapes at the edges of your awareness, are rolling up their sleeves and reaching for the most obvious lever they can find: star formation efficiency. If the universe built galaxies faster than expected, maybe the answer is not exotic physics. Maybe the answer is that stars formed with far greater efficiency in the early universe than they do today. Maybe the cosmic furnace burned hotter and faster in those first few 100 million years, converting raw gas into stars at a rate that no observation in the local universe has ever suggested is possible. In the nearby universe, star formation is a remarkably wasteful process. Only a small fraction of available gas in a given galaxy actually ends up in stars at any given time. The rest just sits there, too warm, too turbulent, too diffuse to collapse. In the Milky Way, for instance, the star formation rate is roughly 1 to 2 solar masses per year, meaning the galaxy converts about 1 to 2 suns worth of gas into new stars annually. That sounds like a lot until you consider that the Milky Way contains billions of solar masses of gas that could theoretically be forming stars but is not. The efficiency, defined as the fraction of available gas converted into stars per unit time, is quite low, typically a few % per freefall time in the densest molecular clouds, and much less averaged across the whole galaxy. The reasons for this inefficiency are well studied and numerous. Turbulence in the interstellar medium prevents gas from collapsing smoothly. Magnetic fields provide additional support against gravitational collapse. Radiation from hot young stars heats and ionizes surrounding gas, creating pressure that pushes material away from star-forming regions. Supernova explosions inject enormous amounts of energy into the interstellar medium, blasting cavities in the gas and driving powerful outflows that can eject material from the galaxy entirely. An active galactic nuclei, the supermassive black holes at the centers of galaxies, can produce jets and winds powerful enough to heat or expel gas across the entire galaxy. All of these processes act as negative feedback, throttling star formation and keeping it well below the theoretical maximum. But what if those feedback mechanisms were weaker in the early universe? What if the conditions in the first galaxies were different enough that gas could collapse and form stars with dramatically higher efficiency? Several theoretical papers published in the wake of JWST's discoveries explored this possibility, and the argument had some plausible foundations. The first galaxies formed from gas that was denser on average than the gas in present-day galaxies, because the universe was smaller and more compact. The dark matter halos, while less massive, were more concentrated. The cooling times might have been shorter in certain conditions, and the feedback mechanisms that suppress star formation today might not have been fully established yet. The first supernovae had not yet had time to build up the turbulent, magnetized, multi-phase interstellar medium that characterizes mature galaxies. The first generation of active galactic nuclei might not yet have grown powerful enough to regulate star formation across their host galaxies. If you turn the star formation efficiency dial up, way up from a few % to 30, 40, even 50%, you could, in principle, produce more massive galaxies in less time. Some models showed that boosting the efficiency by a factor of 5 to 10 could bring the predicted galaxy masses at high redshift into rough agreement with the JWST observations. Problem solved, case closed, everyone go home and sleep well. Except that it was not that simple, because cranking up star formation efficiency had consequences that rippled through the rest of the model like pulling a thread in a sweater. If early galaxies formed stars that efficiently, they should have consumed their gas supply very quickly, producing a burst of intense star formation followed by a rapid decline as the gas ran out. This would leave a distinctive signature in the stellar populations, a galaxy dominated by old stars with very few young ones, what astronomers call a quenched galaxy. Some of the JWST observations were consistent with this picture, showing galaxies with surprisingly mature stellar populations at early times, but others showed galaxies that were still actively forming stars at high rates, suggesting they had not yet exhausted their gas. Reconciling both types of observations with a single model of enhanced efficiency was tricky. There is a fun analogy here, if you're still awake enough to appreciate it. Imagine you're at a buffet and you've been told that most people eat slowly, sampling dishes over the course of an hour. Now someone tells you that a particular guest filled their plate, devoured everything in 10 minutes, and is already going back for seconds. You might explain this by saying the guest was simply hungrier and ate faster. But then you have to explain why they still seem to have food on their plate an hour later, and why other guests who should have behaved the same way are eating at perfectly normal speeds. The appetite explanation works for some cases, but creates new puzzles for others. Scholars still argue whether enhanced star formation efficiency alone is sufficient to resolve the impossible galaxy problem, or whether it is just one piece of a larger puzzle that requires additional ingredients. The debate is complicated by the fact that star formation efficiency is not a single number. It varies with environment, with gas density, with metallicity, with the intensity of the radiation field. Modelling all of these dependencies in the extreme conditions of the early universe requires assumptions stacked on assumptions, and different groups make different choices, arriving at different conclusions. The models are getting better, the observations are getting sharper, but the gap between what we see and what we expected has not yet fully closed. Your breathing deepens, and the murmuring theorists at the edge of your awareness grow quieter, still working, still adjusting their dials, but fading now into the background hum of an unsolved problem. The dials are not enough. You can feel that, even in your drowsy state, the way you can feel a puzzle piece that almost fits but not quite. The edges are close, the colours are similar, but there is a gap, a sliver of light between the piece and the whole, and no amount of gentle pressing will make it disappear. Enhanced star formation efficiency helps. Bigger black hole seeds help. But some researchers looked at the totality of the JWST data. The sheer number of massive early galaxies, the supermassive black holes, the chemical enrichment, the structures that had no business being structured yet, and concluded that incremental adjustments to the existing framework might not be sufficient. What was needed, perhaps, was something more radical, and so the wilder ideas began to emerge, crawling out of the theoretical woodwork like creatures that had been waiting for exactly this kind of crisis to justify their existence. The first and most frequently discussed alternative was modified gravity. The standard cosmological model relies on general relativity to describe the behavior of gravity on cosmic scales, and general relativity has passed every experimental test thrown at it for over a century. But general relativity has never been directly tested in the extreme conditions of the very early universe, where densities were higher, scales were smaller, and the interplay between gravity and quantum effects might have produced behavior that deviates from Einstein's predictions. A family of theories collectively known as modified Newtonian dynamics, or MOND, has been lurking at the fringes of cosmology for decades. Originally proposed in the 1980s by the Israeli physicist Mordechai Milgram as an alternative to dark matter. MOND modifies the law of gravity at very low accelerations, producing effects that mimic dark matter without requiring any invisible mass. Most mainstream cosmologists regard MOND with skepticism, because it struggles to explain the cosmic microwave background and large-scale structure as elegantly as dark matter does. But the JWST crisis gave Mund advocates a fresh talking point. In some formulations of modified gravity, structure formation in the early universe proceeds faster than in the standard dark matter model, potentially producing more massive galaxies at earlier times. Whether this actually works quantitatively, when you run the full calculations rather than waving your hands, is still a matter of vigorous and occasionally contentious debate. Another exotic proposal involved primordial black holes, a concept that has experienced a rollercoaster of popularity over the decades. The idea is that tiny fluctuations in the density of the very early universe, much earlier than the formation of stars, could have been large enough in some regions to collapse directly into black holes during the first fraction of a second after the Big Bang. These primordial black holes would not be formed from stellar collapse. They would be relics of the Big Bang itself, born before atoms existed, and they could range in mass from microscopic to thousands of solar masses, depending on the size of the density fluctuations that produced them. If a population of massive primordial black holes existed in the early universe, they could serve as ready-made seeds for supermassive black holes, bypassing the slow, Eddington-limited growth that makes conventional seed models so problematic. They could also act as gravitational nuclei around which gas would collect and begin forming stars earlier and more efficiently than in a universe without them. The primordial black hole hypothesis is seductive, but it is constrained by a web of observational limits. Too many primordial black holes of certain masses would produce detectable effects, gravitational lensing signatures, distortions in the cosmic microwave background, disruptions of stellar systems that have not been observed. The allowed mass range is narrow, and whether that range happens to overlap with the masses needed to solve the early galaxy problem is not yet clear. It is one of those ideas that is just plausible enough to be taken seriously, and just unconstrained enough to be impossible to rule out, which makes it simultaneously exciting and frustrating. Then there were the truly speculative proposals, the ones that made even adventurous theorists raise an eyebrow. One paper suggested that the fundamental constants of physics, the speed of light, the gravitational constant, the strength of the electromagnetic force, might not have been truly constant in the very early universe. If certain constants were slightly different in the first few 100 million years, the rates of nuclear fusion, gravitational collapse, and radiative cooling could all be affected, potentially allowing faster galaxy formation. This idea, known as varying constants cosmology, has a long and checkered history. It has been proposed in various forms since the 1930s, when Paul Dirac speculated that the gravitational constant might decrease over time. Most physicists are deeply skeptical, because the constancy of fundamental constants is one of the foundational assumptions of modern physics, and the observational evidence for variation is extremely weak. But the JWST data was strange enough that even foundational assumptions were being hauled out for re-examination. There is a quirky historical detail here that captures the spirit of the moment. In the late 19th century, when physicists were struggling to explain the spectrum of black-body radiation, they tried every classical approach they could think of before Max Planck, in what he later described as an act of desperation, introduced the idea of quantized energy. That desperate act launched quantum mechanics and revolutionized physics. Scholars still argue whether the JWST crisis represents a similar moment of desperation that might herald a genuine revolution, or whether it is more like the many false alarms in physics history, where anomalous data eventually found a mundane explanation within the existing framework. The honest answer right now is that nobody knows. The data's too fresh, the models are too uncertain, the stakes are too high for premature conclusions. You lie there in the dark, surrounded by wild ideas, each one a firefly of speculation blinking in the void, and you let them blink without trying to catch any of them. Sometimes the most restful thing you can do with an unsolved problem is simply let it exist, The fireflies blink on, and now you need to understand something important, something that gets lost in the headlines and the breathless social media posts, and the phrases like universe breakers and impossible galaxies. The Big Bang is not broken. You can let that settle like a warm compress on whatever part of your brain has been tensing up with all these challenges and crises and desperate theories. The Big Bang itself, the foundational observation that the universe began in an extremely hot, dense state and has been expanding and cooling ever since, is not threatened by anything JWST has found, not even slightly. The evidence for the Big Bang rests on multiple independent pillars, each one rock solid, and nothing about the early galaxy problem undermines any of them. The first pillar is the expansion of the universe itself, discovered by Edwin Hubble in 1929, when he observed that distant galaxies are moving away from us at speeds proportional to their distance. This relationship, now called the Hubble-Lemaitre law, in belated recognition of the Belgian priest and physicist Georges Lemaitre, who actually derived the theoretical prediction first, has been confirmed by every subsequent observation. The universe is expanding. Run the clock backward, and everything converges to a hot, dense origin. That fact is unchanged. The second pillar is the cosmic microwave background, that faint afterglow of the Big Bang that permeates all of space. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who initially mistook it for pigeon droppings on their antenna. This is one of the most delightful stories in all of physics. The cosmic microwave background has been mapped with exquisite precision by satellites including COBE, WMAP and Planck. Its properties match the predictions of Big Bang theory with an accuracy that borders on eerie. The temperature fluctuations, the polarization patterns, the frequency spectrum, all of it fits. JWST's impossible galaxies do not alter the cosmic microwave background by a single microkelvin. The third pillar is Big Bang nucleosynthesis, the process that produced the lightest elements in the first few minutes of cosmic history. The predicted abundances of hydrogen, helium and lithium match the observed abundances to a remarkable degree, providing an independent confirmation of the hot, dense early state. Again, nothing about the JWST discoveries challenges this. What the impossible galaxies challenge is not the Big Bang, but the Lambda CDM model, which is the specific detailed framework that describes how the universe evolved after the Big Bang. Lambda stands for the cosmological constant, the mathematical term that represents dark energy, the mysterious force driving the accelerating expansion of the universe. CDM stands for cold dark matter. Together, Lambda CDM provides a comprehensive account of cosmic evolution from the first fraction of a second to the present day, including the formation and growth of galaxies, galaxy clusters, and the large-scale cosmic web. It is the standard model of cosmology, and it has been spectacularly successful. But it is a model, not a law of nature, and models can be incomplete. The distinction matters because the public narrative around JWST's discoveries often collapse the difference between the Big Bang is wrong and our model of what happened after the Big Bang needs work. These are wildly different statements. The first would be a revolution on the scale of quantum mechanics or relativity. The second is more like a renovation, knocking down a wall and rebuilding it in a better location. Both are significant, but they are not the same kind of significant, and conflating them creates confusion that serves nobody well, except perhaps the creators of clickbait thumbnails. What specifically needs renovation in the Lambda CDM model is the story of cosmic adolescence, the period between roughly 100 million and 1 billion years after the Big Bang, when the first stars, galaxies and black holes were forming. The model's predictions for this epoch were always its least well-tested component, because until JWST, no telescope could see deeply enough to check them directly. The model was calibrated primarily against observations of the low redshift universe and the cosmic microwave background, with the early galaxy predictions essentially extrapolated from those anchors. The extrapolation, it now appears, was off. Not catastrophically, perhaps, but significantly. The universe assembled its first large structures faster and more efficiently than the extrapolation predicted. There is a useful analogy here. Imagine you have a weather model that does an excellent job predicting temperatures and wind patterns for the continental United States. Someone asks you to use the same model to predict the weather in the Sahara Desert, which the model was not calibrated for. Your predictions might be reasonable, but they might also be off, because the desert has conditions, extreme aridity, unique terrain, different thermal dynamics that the model was never trained on. That does not mean the model is useless. It means it needs additional data from the desert to be properly calibrated for that environment. The early universe is the Sahara, and JWST is the weather station that just opened there. Scholars still argue about how extensive the renovation needs to be. Some believe minor adjustments, higher early star formation efficiency, revised feedback prescriptions, better dust models, will bring lambda CDM into agreement with the data. Others suspect that something more fundamental is missing, perhaps a new physical process that operates primarily at early times and becomes negligible later, which is why it was never noticed in the low redshift data. The optimists point to the many previous crises in cosmology that were eventually resolved within the standard framework. The pessimists, or perhaps the adventurers, note that every genuine revolution in physics was preceded by exactly this kind of persistent, unresolvable tension between theory and observation. The Big Bang holds, the details waver, and you lie in the dark, breathing steadily, riding the gentle oscillation between certainty and uncertainty, like a boat rocking on a calm sea. The boat rocks, and the sea stretches ahead because the telescope is not finished, not even close. You're lying here in what is still the early chapter of JWST's operational life, and everything you have heard so far, the impossible galaxies, the panicking theorists, the spectroscopic confirmations, the wild hypotheses, all of that came from roughly the first year and a half of data. JWST was designed to operate for at least 5 years, with enough fuel to last 20 or more. The mirror is not degrading. The instruments are performing at or above their specifications. The sunshield is intact. The telescope is, by every engineering measure, in excellent health, floating serenely at the second Lagrange point with nothing to do but keep staring into the dark and collecting photons. The best data has not arrived yet. The best data is still out there, falling silently onto the golden mirror, waiting to be read. The observing programs that produced the first wave of impossible galaxies were, in a sense, preliminary. JADES, SEERS, GLASS. These were early release and Cycle 1 programs, designed to demonstrate JWST's capabilities and provide the community with initial datasets to work with. They covered relatively small areas of sky, because deep observations require long exposure times, and long exposure times mean you can only cover so much real estate. JADES, for instance, stared at 2 fields totaling roughly the area of a few full moons as seen from Earth. That is a tiny fraction of the total sky. If those small fields contained dozens of impossibly early galaxies, what would larger, deeper surveys reveal? The answer is already beginning to emerge. Cycle 2 and Cycle 3 observing programs, approved through competitive peer review and drawing on the lessons of the first year's discoveries, are pushing deeper and wider. The Cosmos Webb Survey, one of the largest programs in JWST's first cycle, has been mapping a much broader region of sky at slightly shallower depth, providing a statistical complement to the pencil beam depth of JADES. The results so far are consistent with the earlier findings. Massive galaxies at high redshifts are not confined to one or two lucky fields. They appear to be everywhere, suggesting that whatever process produced them was not a localized anomaly, but a feature of the early universe as a whole. New programs are targeting specific puzzles raised by the first-year data. One program is dedicating hundreds of hours of telescope time to obtaining ultra-deep spectroscopy of the highest redshift candidates, aiming to measure not just their distances but their detailed chemical compositions, gas kinematics, and star formation histories. Another is searching specifically for direct collapse black hole candidates, looking for the spectral signatures of massive gas clouds collapsing without fragmentation into stars. A third is conducting a systematic census of galaxy morphologies at high redshift, using JWST's sharp infrared imaging to determine whether these early galaxies are smooth, clumpy, disk-like, or merging, each morphology offering different clues about the formation process. There is a lovely detail about how JWST observing time is allocated that is worth mentioning as you drift. The telescope is shared among astronomers worldwide through a competitive proposal process managed by the Space Telescope Science Institute in Baltimore. Each year, scientists submit proposals describing what they want to observe, why it matters, and why JWST is the only telescope that can do the job. A panel of experts reviews the proposals and selects the best ones, much like a grant review process. The demand is overwhelming. In a typical cycle, the telescope receives proposals requesting roughly 10 times more observing hours than are available. 9 out of 10 proposals are rejected. The competition is fierce, and the fact that so many of the approved programs in recent cycles are focused on the early galaxy problem tells you something about where the community believes the most important unanswered questions lie. Meanwhile, JWST is not working alone. Ground-based telescopes are contributing critical complementary data. The Atacama Large Millimeter Array, or ALMA, a network of radio dishes in the Chilean desert, can detect emission from coal dust and gas in distant galaxies, providing information about the fuel supply for star formation that JWST's infrared observations cannot directly access. The European Southern Observatory's Very Large Telescope, perched atop a mountain in Chile's Atacama Desert, is contributing optical and near-infrared spectroscopy. And planning is well underway for the next generation of ground-based observatories, including the Extremely Large Telescope, currently under construction in Chile with a primary mirror 39 meters across, roughly 6 times the diameter of JWST's mirror. When the Extremely Large Telescope comes online, it will be able to obtain spectroscopy of objects too faint for even JWST to analyze in detail, extending the reach of the investigation even further into the cosmic dawn. There is a quirky footnote to the naming of these telescopes that astronomers find both amusing and slightly embarrassing. After decades of giving telescopes evocative names — Hubble, Spitzer, Chandra, Webb — the ground-based community has settled into a naming convention that consists entirely of increasingly hyperbolic adjectives. The Very Large Telescope, the Extremely Large Telescope. The original proposal for the next American ground-based telescope was briefly called the Overwhelmingly Large Telescope before the project was scaled back. Scholars still argue whether this trend reflects a charming lack of pretension or a collective failure of imagination, but either way, the telescopes themselves are extraordinary regardless of what we call them. The point of all this, the thing to carry with you as your eyelids grow heavier, is that the story is not over. The impossible galaxies were not a single shocking discovery followed by a neat resolution. They were the opening chapter of an investigation that will unfold over years, perhaps decades, as better data meets better models and the picture of the early universe slowly sharpens. Right now, you're living in the messy, exhilarating middle of it. the part where the questions outnumber the answers and every new observation raises as many puzzles as it solves. The golden mirror stares on, patient and tireless, and somewhere in the dark new photons are arriving. The photons arrive and they carry with them something heavier than data. They carry a feeling, a shift in the way you relate to the universe and your place in it. You're deep in the pillow now, deep in the dark, and the technical details are beginning to soften at the edges, blurring into something more contemplative, something that has less to do with stellar masses and redshift calibrations and more to do with the ancient human experience of looking up at a sky you do not fully understand. Because that is what this is really about, underneath all the jargon and the simulations and the frantic preprints. It is about what happens when the universe turns out to be stranger than you thought. And it is about what that strangeness means, not for the models, but for you. There is a word in the philosophy of science that describes the moment when an established framework encounters an observation it cannot accommodate. The word is anomaly, and it was given its modern meaning by the historian and philosopher Thomas Kuhn in his landmark 1962 book on the structure of scientific revolutions. Kuhn argued that science does not progress in a smooth, linear accumulation of knowledge. Instead, it alternates between periods of normal science, where researchers work within an established paradigm and solve puzzles consistent with that paradigm, and periods of crisis, where accumulated anomalies strain the paradigm to its breaking point and eventually trigger a revolution that replaces it with something new. The transition from Newtonian mechanics to Einsteinian relativity was one such revolution. The birth of quantum mechanics was another. Each was preceded by a period of mounting tension between theory and experiment, a period where the old framework kept almost working but not quite, where patches and workarounds proliferated, where the smartest people in the field could feel that something was about to give, but could not yet see what would replace it. Whether the JWST impossible galaxies represent a genuine Kuhnian crisis is one of those questions that can only be answered in hindsight. From inside the moment, it is impossible to tell the difference between a genuine paradigm shift in its early stages and a dramatic but ultimately resolvable anomaly. The feeling is the same: the excitement, the anxiety, the proliferation of speculative ideas, the sense that the ground is shifting under your feet. Scholars still argue whether any of the proposed alternatives to lambda CDM are mature enough to constitute a new paradigm, or whether they are still in the stage of vague gestures towards something that has not yet crystallized into a coherent theory. The honest assessment as of now is that lambda CDM remains the best available framework, but it has a conspicuous bruise, and the bruise is not fading. And there is something beautiful about that uncertainty if you let yourself sit with it instead of rushing to resolve it. The history of astronomy is, in many ways, a history of humility. Every major advance has involved the discovery that the universe is larger, older, stranger, and less centered on us than previously assumed. Copernicus moved the Earth from the center of the solar system. Hubble showed that the Milky Way was one galaxy among billions. The discovery of the cosmic microwave background revealed that the universe had a beginning that predated all human mythology. The detection of dark energy showed that the expansion of the universe is accelerating, driven by a force that constitutes roughly 68% of the total energy content of the cosmos, and whose fundamental nature remains completely unknown. Each of these discoveries was initially resisted, debated, and gradually accepted, and each one left humanity a little smaller and the universe a little more magnificent. The impossible galaxies fit neatly into this tradition. They're telling us that the early universe was more dynamic, more creative, more capable of building complex structures than we gave it credit for. The cosmos did not sit in quiet darkness for 1 billion years after the Big Bang, slowly and cautiously assembling its first primitive galaxies from tiny building blocks. It got to work immediately, with an urgency and efficiency that our models failed to predict. There is a strange comfort in that, if you tilt your head the right way. The universe is not lazy. It is not timid. It is an engine of astonishing productivity, and it was productive from the very beginning. There is a quirky aside here that might make you smile as you drift. The philosopher Immanuel Kant, writing in 1755, proposed that the fuzzy nebulae visible in the night sky were actually island universes, vast collections of stars comparable to the Milky Way but vastly distant. He was right, but it took nearly 200 years for observations to catch up with his intuition. Sometimes the universe outpaces our instruments by centuries. Sometimes, as with JWST, the instruments outpace our theories by decades. The mismatch in either direction is where the interesting stuff happens. You're breathing very slowly now, and the feeling that settles over you is not anxiety about the unknown. It is gratitude. Gratitude that you live in a time when a golden mirror floating 1,000,000 miles from Earth can show you the face of the universe as it looked 13 billion years ago, and that the face is more surprising, more intricate, more alive than anyone expected. Gratitude that the mystery is not yet solved, because unsolved mysteries are what pull us forward, what make us build telescopes and write equations and lie awake at night wondering. The day every question has an answer is the day the story ends, and you are nowhere near the end. The impossible galaxies glow faintly in your mind, not as problems to be solved, but as invitations to look more carefully, to think more creatively, to hold your models lightly and your wonder tightly. The universe is under no obligation to make sense on your schedule. The invitation hangs in the dark, soft and open, and now the light begins to dim even further, not because the galaxies are fading, but because you are. Gently, willingly, the way a candle flame lowers itself into the wax at the end of a long evening, not extinguished but simply settling, becoming quieter, becoming smaller, becoming warm. You're still out there in the void, floating among the ancient photons, but the void does not feel empty anymore, it feels inhabited, populated by light that has been travelling since before the Earth existed, before the sun ignited, before the Milky Way assembled its spiral arms from the merging debris of countless smaller galaxies. That light is still arriving. Right now, as you lie here, photons that left their source 13 billion years ago are landing on the golden mirror at the second Lagrange point, ending journeys that began in a universe unrecognizable from the one you inhabit. And the mirror catches them, gently, the way a cupped hand catches rain. Think about that for a moment. A photon leaves a young star in a galaxy that should not exist. It travels through expanding space for 13 billion years. It crosses voids where no matter exists for hundreds of millions of light years. It passes through the intergalactic medium, through filaments of the cosmic web, through the thin halo of the Milky Way, past stars that had not yet formed when the photon began its journey. It enters the solar system, passes the orbits of Neptune and Jupiter and Mars, slips past the Earth, and arrives at a mirror that a species of upright primates designed, built, folded into a rocket, and launched to a point in space precisely calculated to receive it. The photon does not know any of this. The photon has no experience of its journey, because from the photon's perspective, travelling at the speed of light, no time has passed at all. For light, departure and arrival are the same moment. 13 billion years of travel compressed into an instant. There is something almost unbearably poetic about that, and you're allowed to feel it without needing to understand the mathematics behind it. The galaxy that produced that photon, JWST 13-0, our stubborn, impossible, magnificent smudge of ancient light, is long gone in any recognizable form. 13 billion years of cosmic evolution have transformed it beyond recognition. It has merged with other galaxies, been disrupted by gravitational encounters, had its gas stripped and replenished and stripped again. The stars that were shining when the photon left have long since died. Their heavy elements scattered into the interstellar medium, incorporated into new stars, new planets, perhaps new chemistry. The galaxy's descendants are out there somewhere in the modern universe, embedded in some larger structure, their ancestry written in the chemical signatures of their oldest stars but otherwise invisible, untraceable, lost in the crowd. You cannot point a telescope at the sky and find what JWST 13 became. You can only see what it was, preserved in light, like a photograph of a great-grandparent you will never meet. And that is the thing about observational cosmology that makes it unlike any other science. You cannot experiment on the universe, you cannot rewind it, you cannot set up a control group, you can only watch, and what you watch is always the past because light takes time to travel. Every observation is a memory, every image is a ghost. The deeper you look, the further back in time you see, and the objects you see no longer exist in the form you're observing them. The entire enterprise of cosmology is built on the testimony of light that has outlived its source, and there is a quiet melancholy in that, a sweetness threaded with loss, like listening to a recording of a voice that has long since fallen silent. Remember that tightrope walker from earlier? The one performing without a net over a very deep canyon? The astronomers are still on the wire. The spectroscopic confirmations steadied their footing. The enhanced star formation models gave them a longer balancing pole. The exotic hypotheses are the safety nets they are weaving below just in case. But the walk is not over. The far side of the canyon, a complete self-consistent understanding of how the universe built its first galaxies, is still out of reach. It might take years of additional JWST data to get there. It might take the extremely large telescope, or some instrument not yet imagined, or a theoretical insight that has not yet occurred to anyone. The history of science teaches us that the answer, when it comes, will probably be something nobody predicted, something that seems obvious in hindsight but was invisible in advance. That is how it always works. The universe does not give spoilers. Scholars still argue, and they will argue for a long time, and that arguing is not a flaw in the process. It is the process. The back and forth between observation and theory, the tension between what we see and what we expect, the willingness to be wrong and to start over, that is how knowledge grows. Not smoothly, not efficiently, but stubbornly. The way a tree grows through rock, finding cracks and pushing through them one slow a millimetre at a time. And now the story softens. The technical language dissolves like sugar in warm water, leaving only the sweetness behind. You are lying in the dark, and the dark is kind. The impossible galaxies are still out there, glowing in the infrared, older than anything you will ever touch. And they do not need you to explain them tonight. They have waited 13 billion years. They can wait until morning. Your breath is slow and deep, rising and falling like the expansion and contraction of a very small, very personal universe, the one contained within your ribs. The golden mirror floats in your imagination, catching light, catching time, catching the whispered secrets of a cosmos that is vaster and stranger and more beautiful than any model has yet described. The photons fall like snow, silent and weightless, each one a messenger from an age before the earth, before the sun, before the heavy elements that built your bones. You're made of the same stuff those ancient galaxies were forging in their impossible furnaces, the carbon in your breath, the oxygen in your blood, the iron in your heart. You are, in a sense, the universe looking back at itself across 13 billion years, drowsy and wondering, not needing answers tonight, just needing rest. The stars dim. The data streams slow to a murmur. The golden mirror holds its vigil, patient and steady, and you drift, and you drift, and the ancient light keeps falling softly, softly, all the way down into sleep. Good night. Sleep well. The universe will still be impossible in the morning, and that is the most wonderful thing about it.